Hey guys, today we're going to be showing you how to use these logic gates and build a boat for treasure. This will also work on logic gate websites and stuff. First is the AND gate. It checks if every switch is on. So if every input is on, the output will be on. Next is the OR gate. It activates when at least one is on. So if you activated 2, it would be on. If you activated 3, it would be on. At least 1, it would be on. Next is the XOR gate. It activates when an odd number of switches are on. By the way, the websites don't let you use multiple inputs, only 2. And lastly is the NOT gate. And this is a NAND gate, but this is demonstrating a NOT. So NOT just inverts the output of any gate. So you just add an N to the beginning, then it will invert. So this is a NAND gate, so it will only activate if it's not AND. So if I do it, if all are on, then it turns off. Then a NOR would be when none are on. Then an XOR would be when not an odd number of switches are on. I mean when an even number of switches are on. Next is a tutorial on how to build an SR latch. This is a memory component. It will help you a lot. So you want to place down 2 logic gates. Change them to NOT and OR. Wire them up to each other like that. Hook up buttons to both of the inputs. Then whichever input is on, it will invert it to the other side. And you can't change it after clicking it so many times. This is commonly known as an SR latch because if you attach one output, then it will set S or reset R. Just mess around with that and you'll understand it. Next is how to build a T flip-flop. First, I'll teach you how to build a monostable circuit. Because you need to learn how to build a monostable circuit for most of these. You want to place down 2 AND gates, one a NOT AND and one an AND. You wire the button up to both of them. Then you wire the NOT AND up to that. So it will only activate for 1 tick. Then you want to get your logic gate and change it to XOR and AND. Then you wire this up to this and then this up to that and like that. Then this is a T flip-flop. It will just change the output of whatever you want. It will just invert the output when you click the button. Next is how to build a binary counter. We'll use SR latches for this. So a bit is something you have to understand. A bit is a form of data. So in binary, it does 1s, 2s, 4s, 8s. You just times it by 2 for the place values. A bit is 2 to the power of whatever, how many bits you have. So for this example, we'll build a 2-bit binary counter. So build 2 SR latches. Then place AND gates, like 3 for each side because we have 2 bits. Then wire these up to the opposite side. Wire the ones that are next to these ones to the opposite side. Then you want to wire these up to each other. Then you want to wire these back and forth like this. This is called an up-down binary counter. But you need to build a monostable circuit first. So let's build one. So you want to have a NOT AND and another NOT AND. Then you want to wire the NOT AND the button up to both of them like this. Then you want to wire the NOT AND up to the AND. Then that's the smallest monostable circuit. This is the down button. It counts down. Well, this is a debugging thing. See how it doesn't work? This is, you have to debug. So, in my case, I don't know what's the issue. It's because I didn't wire that up to the not and up to this. You have to make sure you wire everything up to each other. Then this is a down button. It counts down in binary. Remember, 1's 2. So this would be 1 plus 2 would be 3. 0 plus 1. 0, 1 would be 2 because this is a 2's place. Then this right here would be 1, 0, which would be 1 because this is a 1's place. Then there's then you have 0, 0, which would of course be 0. Okay, I just simplified this that we have more room for the decoders. I just moved these up to each other like this. Then they are still the same thing, it's just that, because look, both of these are wired up to that and that's wired up to that. This is a monostable circuit. It's still a monostable circuit. Then for decoders, you'll want to know how many outputs there are. So 2 to the power of how many bits there are. This is 2 bits since there's are two outputs. So now 2 to the power of 2 would be 4. So I have 4 outputs. So I place down 4 AND gates. Then for 0, I would just wire both of them up to this one. These orange ones up to the first one. Then I would wire these orange ones up to the second one. You just want to count up and then see what numbers are next in binary. So then this one would be these two. And then so on and so forth. Then now you have a selector panel. Then to hook this up to displays, you would want 4 displays like this. I'll paint them black for this example. Then I'll make the selector panel. So you'll want to hook up knots to the end because display blocks in Build-A-Boat for treasure they save whatever's on it. So I'll color these knots black because whenever it's not on, it will be black. Then you wire the knots to the displays. Then you color whatever you want the decoder's colors to be like that. Then look, you have the selector. This can also work for a snake game. So if you had a clock just ticking and then seeing which direction you're moving in with SR latches, then you will see that this goes up and then the snake will move right and it will also loop around. But if you don't want it to loop around, you can just get rid of one of these and make that the game over. Next, let's build a simple snake game together. So I'll use 4 bits because I want a 4x4 grid. I'll build a binary counter like you were taught. Just like this. And I'll just skip to when I'm done. Okay, this is a binary counter. I still have to build the monostable circuit, but if you haven't watched the other part of this, then you should have, and you shouldn't have skipped. And you want to wire these up to both of them for the monostable circuit. Then you have an up-down binary counter. This will change the directions. We're building a simple snake game right now. This is a 4x4 grid since we have 2 bits, and 2 to the power of 2 would be 4. So now we want decoders. And I'll decode every single one because remember, all that are on. You don't want to forget one bit and then have it on 2 at a time on at the same time. Then now we want to duplicate this for the Y position. The Y position will store the snake's up and down position. The left and right position is the X position. Now we build a 4x4 grid. But by the way, this snake game won't have any tails. We're not making the tail just yet. Then you want to have OR gates with the color that you want hooked up to every single one. I'll move these back so it's a little simpler. Then you want OR gates for each X and Y position. That this is adaptability for the tail. Then you want to color this like that. For this example, I'm going to use this color, but you can color whatever color you want the snake to be. Then you want to make these have knots. So you want these to be not, so that it inverts the output and turns off the lamps when it's off. Then for the head, we're going to add some AND gates to check if the X and the Y position are on this level. So for example, I did this and layer 1 Y position. I did layer 4 X position and layer 1 Y position. So if both are on, because look, if I go back, it will display it on the screen, and when I'm not on it, it won't display it. So now you'll want to change the X positions to have this, and these are all layer 1s. So now look, that's a bug. Bugs are bad in coding. Then let's see what the problem is. So these are all layer 1s, and these are being hooked up to the screen, so that's why. These have to be hooked up to those. Then look, you have a working 1-layer snake. Then for the upper layer, you'll want to duplicate this up more. Just up 1 more pixel, and then duplicate this again for the more pixels you have. Then now I'll hook up the ORs to the things and the knots to the pixels. So I'll just skip to when they're all wired. So they're all wired now. Now we have to check layer 2 X position, Y position, and then remember, Y position will just be the up and down position. So for example, this one would be all of these, because that's layer 1 Y position. Then for this, we want to wire up these. So look, now it displays layer 2. But remember, layer 2 is different than layer 1. And these just go up like this in a pattern. These go up in a pattern, like going up with X and going down with Y. But Y just stores which position it is in. So now we're going to wire all of these up. Don't mind if the pixels are getting weird. That is just because you have nothing wired to the AND gates too. So now I wire layer 3 up to that, and then layer 4 up to the one above it. Then we have workings up and down snakes. Just the head though. You can adapt it to use the tail too. You would just need to add a buffer layer. We'll talk about that in another episode in the future. I forgot to move these, so I'm moving them back. So now we're going to talk about making the thing move. So for making it move, we want to store the movement direction in a SR latch, so they only have to click the button once to go. Then we want to have an XOR gate and AND gates. Just one XOR gate and AND gates before every single one. We will check XOR if only one position is wired. Pressed at a time, then it will let it go. So then we want to wire these. For example, I'll use WASD up, down, left, down, right. Then now we wire these up to here. After wiring the directions up to the XOR gates, we'll want to wire the XOR gates up to these ANDs. Then we'll want to wire the ANDs also WASD, so that if the button is pressed and only one of them is pressed, then it will let it move. So now we can replace these buttons with OR gates, checking if one or the other is on. Wire these up to the monostable circuits. And delete the buttons afterwards. And change these to OR gates too. Then now you have OR gates for the inputs for the binary counters. And by the way, this right here, the AND gates, is called a matrix. A matrix is just a value of checking ANDs. So for pixels on the screen. So I have 1, 2, 3, 4, and I have 1, 2, 3, 4 going up. Then, now back to this. We want to set these once we get the signal. Then we have W, so we'll send. Wait, these are supposed to be AND. And then you'll want to send the signal to the AND. So the reset. So W would be up, A would be left, S would be down, and D would be right. I think these are right, but we'll see once we get them working. Then we'll also want to have a clock. Checking if the clock is ticked, then it will turn off. If the clock is ticked, then it will go to the next pixel. I'll change this clock to 0.4 pixels. You want to wire the clock up to each other. Make sure this is a button wired up to the clock. Then start the clock. Then it will check if we need another monostable circuit. So I need a not and. These are both wired up to each other, then this is wired up to that. Then we have a clock ticker. It will check if the clock ticks and this is pressed, then it will go. So left is not left, so I'll invert left to be this one, and right to be this one. Because look, now left is left, down is still, it's moving in a diagonal, so we gotta fix that. This is because two inputs are on, as you can see right here. To fix that, we will want these ands to reset every other one. Reset every single other one. So you'll want to wire these up to the reset button of every other one. And now look, we have a snake, but it's still doing that. So we want to make sure that we wired every other one to the reset button. And we want to reset the one that's on, because that's not supposed to happen. And reset the one that's on, and reset this one. Remember, making logic gates and code is always has bug fixes. So this is just a simple head working. And we'll move on to the next example, but the next example is already pre-built. So we'll take a look at the wirings. Next, we have tic-tac-toe. So to make this work, we will check it. We will see if the button is pressed and the game is not over, then it sets it. But this, you can still override stuff, because this is supposed to make it not override the occupied check right here. But you have to make sure that if it's not occupied and that is on, then it will not be occupied. Then you can't occupy it. But that's the whole premise of this. It checks this one, then it occupies it and plays it over here. It occupies it, plays it for blue. Then it will check if it's not, that square is not occupied, and this is on for each one, then it will occupy the square and display it on the screen. I mean, not occupy the square, it will just display it on the screen and write it for wind detection. Then this is wind detection. It uses SR latches to store everything. Then it uses each possible win combination, which there's 8 in tic-tac-toe, all of these. Then you'll want to check if they're not win. Then it will send that back to the beginning, like I said, not win. Then it will check if every square is filled, like if every square is filled and it's not a win, then it will display a tie. And it should reset, but it's not wired to that. Okay, so this is basically the whole premise of tic-tac-toe, and this is the end of this video. Thank you guys for watching, and bye.